Uh, so last time we talked about something about one of the algorithm belongs to like belonging to the supervised learning algorithm. And today we will talk another type of algorithm which belongs to unsupervised learning algorithm, which means that we don't need labels in the data set. And obviously, our our theme in this lecture will focus on one type of the most popular unsupervised learning algorithm. It is dimensionality reduction. And PCA, as we know, principal or components like analysis is just one of the side of we can call it one of the side of the algorithms which comes from one type of the dimensionality reduction. And before that, we will just combine the code we have on the GitHub, and we will explore some basic knowledge under the hood, which will help us to just grasp the hyperparameters and also the attributes we have when we just call them in Python. After knowing what it refers to in math world, and we will know how to apply them when we are in our project. So before talking something about PCA, we should be aware of what does it mean when we are using the algorithms which is classified into dimensionality reduction. Let's see the right side on this screen. And as we all know, we live in a three-dimensional world. So it will be counterintuitive when we are going to imagine something happens of just generating in a four-dimensional space, let alone more high-dimensional space. So one of the tasks for us to do in machine learning is to we just going to abstract some rules in real world, which is composed of high dimensional features, and we just grab them from the real world, and they will just construct a feature space as we have mentioned in the last meeting. And the mission for us is to find the connections or find the relationship between the mathematical world and the real world, which means that we should need to find some rules that bridge us in mathematical world and the physical world. And those rules are hidden in a high dimensional feature space. So this is why one of the reasons why we need to do dimensionality reduction. And also the problem when in high dimensional world is the curse of dimensionality. The curse of dimensionality. It means that the higher the dimension is, and the more likely it would be to get closer to the border. So we can see this picture here. Like when we put cat and dogs in two-dimensional space, and it is quite easy to draw a circles and to just include all of the animals here in this square. And when it comes to a three-dimensional feature space, and you need to just draw a sphere, or not a sphere, like you need to just draw another scene to include them. But as you can see, when they are in two-dimensional space, they are squeezed and they are crowded. And in a third-dimensional space, they scattered. And also, if we put them in a more high-dimensional space, they will scatter heavily. And if you just start to confirm it, you can start from the mathematical view. And just like when you pick one of the number randomly inside a specific square, and most likely to be lie down or inside the square, not as close as to the border. But if we are in a high dimensional space, all of the numbers you pick will be more likely to be close to the border. So it's one of the it is one of the attributes that the high dimensionality has. This is why we need to do this dimensionality reduction, because it has a risk of being sparse in high dimensional data sets, which reflects in our machine learning job, because more dimensions will mean the risk of overfitting. Especially we talk something when we talk something deep learning, when we are using some tree models, like last time we have talked something or maybe next time we will talk something about random forest, which is one of the algorithms of ensemble learning. And more dimensions, which means it will be prone to be overfitting. Because if you use the algorithm which have great generalized ability, and you will be prone to be overfitting. But also, as we can see, if we just put all the dog and cat in one dimensional space, like we put them in a line, it would be hard for us to classify them. Once we put them in a two-dimensional space, and it will be more easier for us to use some algorithm like the linear regression to make a classification job. And that is not enough. When we just increase the dimensions, and maybe it will help us to get more classification score when we are applying more just complex algorithms, like we talked, the tree models, and also like the artificial neural network. And maybe next time we can just use that. So one of the solutions to avoid the dimensionality, to avoid the curse of dimensionality, is to increase the data set size. We should ensure that it should be sufficient density in high dimensional space. But the fact is that as the size of the data size increase, as the dimensions increase, the data size should increase exponentially. So it is just unrealized for us, and it's not easy for us to use this method to solve the curse of dimensionality. So almost, or in most cases, we will just abandon this method, usually. But if you can get a huge data set to ensure that, and you can just explore them in high dimensional space. But if we can't, we should try another, like we should try other ways to solve this problem, the curse of the dimensionality, even if it can help us in some ways to do a better regression or classification job, but it will be prone to be overfitting when we use some algorithms which has a have a great generalized ability. So we should seek other solutions to solve these problems. How can we do that? Like there are two other options we can choose. Like the first one is the feature selection algorithms. And this is also many machine learning projects would do, because we need to note which features will be more important and which features will be more dominant when we use them as the features to make prediction. And there are a bunch of algorithms which can do that job. And most of them are example learning. Like we know the random forest and actor tree and other things like the target boost, and all of them belong to example learning. So it's for us to this job it's for us to just fix the problem caused by the curse of dimensionality. Is to use the feature selection algorithm, which will help us to select which one will be important and which one would be useless, and we can drop those kind of useless features, which is, in other words, it will help us to decrease the number of the features, and which means that we will do a filtering job to help us to decrease the dimensions of the feature space. And the last one solution for us to do is to use the feature extraction algorithms. And we'll talk later. PCA is one kind of those feature extraction algorithms, and it belongs to projection. Because when we are trying to use dimensionality reduction, there are two common ways we can do. One is projection, and the other one is manifold learning. So then we'll just go deeper to explore how we can use PCA and how we can note what's the distinctive difference between projection and manifold learning. But before that, any question, if you have. Feel free to ask any questions if you have. Okay, if there's no any problems, then we just move on. And on the left side, you can see the code, and also you can download it from the public GitHub channel. And it's quite normal because we have put this as a setup. So every code, every small project I wrote, and I will put these kind of things at the top of the whole notebook. And you can see it as setup, so we can just ignore it. And then it's quite just normal for us to use the pandas to read the Excel, because the data are stored in the Excel sheet. And then, because usually I would put the label and the features together inside one sheet. So the job for us to do is to just drop the true value, which is labels. Because I have mentioned that this is because days we are going to apply unsupervised learning, which means that we don't need labels. So we don't need this true value in the data set. So we need to drop this calling. And before we go deeper, we should note, mostly when we are applying unsupervised learning algorithms, it's just as a preparation. It is just the preparation for the sequent work we will use by supervised learning algorithms. And once you have once you have idea about the other ones of the unsupervised learning algorithm, like the clustering, and you will know that it will just be part of your project, and you will just be put before the real supervised learning algorithms. So you must keep that in mind when you are going to use unsupervised learning algorithms. In most cases, you will just put them before the supervised learning algorithms, because it can do some job for you to make a better analysis on the data sets you have. And it will just be used also when we are trying to realize the PCA, and we should put that before supervised learning algorithms. Okay, so the pros and cons when we are doing dimensionality reduction, as we can see that it may help us to filter some noises and some unnecessary details, and which will help us to get a higher performance and speed up the training time. But it's just one of the way it can do, and the con is that it may lose some information, and you will cause worse performance. So it seems like an equilibrium. So you cannot get fully guaranteed that when you apply dimensionality reduction, and you will get higher performance. You should try thousands or not thousands of, you should try many tens or hundreds of combination of different algorithms and different hyperparameters. So when you grasp all of those algorithms, and when you are getting accustomed to the steps of machine learning, and the final job for you is to tune your model. You should tune your hyperparameter, and it will be such a long and maybe kind of tedious job for you to do, because the right thing for you to do is to try various combinations among different algorithms and different hyperparameters. But if you are doer, when you just do a lot of projects and you just meet a lot of various circumstances, and you will just cultivate your intuitive to know which algorithm will be better when you want to just fulfill this function, and which hyperparameter would be more better, or would be more reasonable for you to use in this project. And it will help you just to save your time when you get used to those algorithms. So this is why it is critical for us to know what's the difference between between each algorithm, and how can we apply that, and what consequence or what effect it will make if we just apply them. Now we are going to the two normal ways when we want to just do dimensionality reduction. The first one is projection. It's kind of easy to learn because when here, as you can see, these are dogs. These data dogs scatter in three-dimensional feature space. And we just do the job to put them into a hyperplane like this. It's a great one. And then we just project all of the data in three-dimensional space into a two-dimensional square or two-dimensional hyperplane. Why we should do this job? Because sometimes the features are constant, and sometimes some of the features are highly correlated, and this is why we need to do projection. And this is quite common when we use some statistical strategies to fix them, because some of the features are highly correlated and they cannot be characteristic for us to see them as independent features to make prediction. And also, as we can see that maybe the feature instance, they lie within a much lower dimensional subspace of the high dimensional space, because they seems like scattered in somehow in such a somehow rule in a three-dimensional space, because they are crowded and they are just put together. So when you just project them into a two-dimensional space, and you can see the features this feature is not what we taught. Are the features and the similarity between them, just the similarity between them, between what they perform in three-dimensional space and what they performs in two-dimensional space, they are quite similar. As you can see that, like the shape of them, and maybe the relationship, the space relationship among them are quite similar, which represents that maybe those data dogs just perform as well as in a lower dimensional space, and which is why we want to use projection for our project, because maybe they lie within a much lower dimensional subspace of the high dimensional space. And now we'll explore another one, which is manifold learning. Like, if the data sets look like as these pictures show us, which is also one popular models, and which names you can call it Swiss law. And it's one kind of the popular models for us to apply manifold learning. And also it's one of the dimensional reduction. When we are applying a manifold learning, we have a manifold hypothesis, because we think that most real-world high-dimensional data sets lie close to a much lower dimensional manifold. like this. And this is one of the reasons why we need to use manifold learning rather than applying projection. Because if you just simply use projection as we did in the first one, like we create a hyperplane in 3-dimensional space and we project all the data onto it. And it will be a fault if we want to use the same, like the same tag. If we are using the same tag projection to do this job, if we create a hyperplane in whatever angles in this 3-dimensional space, and you can imagine that if we create a hyperplane here, and actually you can get a 2-dimensional just pictures like this, but it cannot truly reflect the attributes this data set has, because the data set is just like a Swiss roll. So for us, it's better to use manifold learning because you will unroll the data sets, and like on the bottom row, on the right side, and you can see these 2-dimensional pictures. And it is the result of the manifold learning. And when we are applying manifold learning, and we can get this result. And you will unroll this data set, and you will got a better performance if we just apply supervised learning algorithm like some classification model, like the SVM, or like we can use some regression model to reflect some of the relationship between them. So this is why we have 2 different methods to do dimensionality reduction. So for us to do is to figure out which one will be better. And when we are going to apply different methods of dimensionality reduction. And then we will talk something about the PCA and what under the hood of PCA, which are just one common type of the methods of projection. Now, it's time for us to go into what projections means and which algorithms would be the characteristic of this algorithm. Like as we can see in most machine learning project or in most statistical analysis, we would use principal component analysis. And the mathematical magic behind that is also quite simple. If you use some basic knowledge when you are learning like some when you are learning statistics and other things, it's quite basic knowledge when you are learning that. And also, it will use the same method SVD, and we will talk then later, to just get the principal components. This is why it calls principal components. And the essence of it is quite simple also. It's just to identify all the hyperplane that lies closest to the data and projects the data onto it. And this is the essence of PCA. So we have an example here. As we can see, if we have the data set which scattered in a two-dimensional space. And how can we do PCA? And firstly, it will select the axis that preserves the maximum amount of variance. The maximum amount of variance. And it is like, I don't know how to explain that, but because it's, I think you have idea on it, because when it comes to the statistical term, there's standard deviation and variance, and which reflects how close is to the mean value and something like that. So it's variance, and it works here too, because we have the awareness that when we are applying dimensional reduction, and we will lose some information. So how can we keep the information as complete as we have in a data set? In a mass term, it will be variance. So when we preserve the maximum amount of variance, and which would mean that we will preserve the maximum information in this dimension. So for the urgency, the PCA would do is to find the axis, and then after it find the maximum amount of variance, and it will do that again, and it will repeat it to find the second one. And then, so that it will just find the third one, fourth, a third one, and fourth one, and fifth one. And also you can see that it just going to select the axis that minimize the mean square distance between the original data set and its projection onto that axis. Because if, as you can see, this solid line, this is a solid line, and this C1, and this is a dotted line, C2, and this is a dashed line, and we can call it C3. And these three axes, if find, after finding them, it will just project the data onto this lines if find. Like at first time, it will find C1 or solid line, and here it will just project all the data onto this line. And then when it finds the dashed line C3, and it will project that onto this line. And so on when it comes to the C2, the dotted line, and it will do the same job also. So the process, or this is how it to evaluate when you select the axis. It depends on the amount of the variance every axis has. So it's not arbitrary to choose, or it's not random to choose the axis. It will count on some mathematical formula behind that. And we will just to go deeper to explore what it really works behind it. And here is the process to do a complete PCA job. Firstly, it will identify the axis that counts for the largest amount of the variance, and then it will find a second axis. And note that it's orthogonal to the first one. It's orthogonal to the first one, and that accounts for the largest amount of remaining variance. And if we have like a 10-dimensional, if we have 10 dimensions, and you will do it again until it finds 10 axes which keep the variance, and it will stop and it will end up. And this is how PCA works. So how can you do this job? And what math and words are the math formula it use when it do this job? Is the standard matrix factorization technique. And you have seen it. You have seen it when we have the meeting on the linear regression, and it's called SVD, singular value decomposition. And it will just simply decompose the X is the Chinese set matrix and into a matrix multiplication of three matrices. V, here V contains the principal components, and principal components represents the axis we find. And one axis means one principal component. And here, the more dimension you have, and the more column the V would have. And this is one of the common solutions when we are applying numerical method to solve some questions. And it's one of the numerical method to do it, and which is different from the closed form method. And how can it project to hyperplane? And also it quite simple one. It can be represented here in this formula. You just compute the massive multiplication of the Chinese set matrix X by the matrix W. And the W here, you can see, is the matrix, and also which contains the first D principal components. That is like the matrix composed of the first D columns of V. If you're getting used to the matrix and also the vector and something else, and you will know what I mean here. And it's not difficult to understand because it's quite simple methodologies. And now we'll just go back to the code we have. So how can we use PCA? It's quite simple because it has been packaged already. And you can just call them by using scikit-learn decomposition PCA. And before that, there's something you should know. We should use the standard scalar to just deal with the data set. And maybe you have be aware of the standard scalar because you have some meeting with the original statistical group, and they have talked something on the pre-processing of the machine learning project. And maybe they are supposed to tell you something on the common package we have in scikit-learn when we are dealing with the pre-processing job. So before we use the PCA, we should use the standard scalar to the whole data set. And what it will do, it will just do a standardized job. And it will just do a zero center, and then it will just do normalization. Why we do that? Because as we know, if you just if you learn something about physics, and maybe you use dimension analysis. These dimensions is not the one we talked previously. It's not like the dimension we talk here. We are using dimension analysis when we are dealing with some questions, with some physics questions. Because we know every features or every value is like the length and width, and they have their own magnitude. And so for us to do is how to just evaluate the result we will get if we just use the magnitude and also the dimension it has. So the standard scalar will do a dimensional list analysis on it. And it will just erase the magnitude among various features. And as you can see that it will help us to put all of the feature at the same level. Because before we apply the feature extraction algorithms, or before we just use the feature extraction algorithms, we have no idea which features will be more important than other ones. We have no idea about it. And this is why we cannot just make some assumption before we do it. And this is why we need to do the non-dimensional analysis by the standard scalar. And what we talk dimension here is different from the ones we talked previously in this part. And it's the term when we are learning physics. Now, it's quite simple for us to just use this packaged PCA. And in scikit-learn packages, it will assume that the original data set is centered, which means the data set will be centralized automatically. Even if you didn't do this job before, the centralization and the PCA will do it for you automatically. And the hyperparameter n components would be quite easy to understand. It represents the principal components. It represents the axes you want to identify, the axes or the principal components, and which these n components hyperparameter reflect to. And this is why I think it's quite important for you to know something under the hood before just call these algorithms package already in the scikit-learn library. Because if you have any idea on this technology, and then you have any idea on what you will do, like secretly. And this is why we should combine them together, and which is why it would be more efficient for us to use them. And when you call these algorithms here, and you can just use the feed transform method on the process dataset, because we have used the standard scalar to the x, and which is x, and X is the data set we read from the Excel sheet. And we have dropped the true value, and the variable is X. Now we are dealing with X, and we have just processed it. We use the standard scalar and we name a new variable, X processed. So when we are going to use the PCA, we should apply them on this variable, X processed. And we can just use fit transform, and it will transform the X processed dataset. Because it's quite simple here as a variable, but it represents a data sheet, maybe in the form of the pandas data frame. And so you need to learn something on the NumPy and also something on the pandas. And I have just kept or emphasized before, because it would help you to understand what it represents here. And fit transform is just the common methods when you are calling some packages from the scikit-learn library. It is like the construction of it, and fit and transform and fit transform. So you should know what it refers to. And then when you call this one, it means that this model or this algorithm has been trained. And now you can just call its attributes like this, the components. Because we just set two here, we set n components to here. And if we call the attributes, you can get two components, two principal components. And like this one, it's also a matrix, and it will be in an array of NumPy. It's a NumPy array. So it's why important to know something about NumPy. And this is the first component. These PCA algorithms identified in this data set. And you should connect them with what you have learned before. This is the first one component, the PCA identified in the X process dataset. And this is the second one, because we set the n components to, which means it will just has two principal components. Why we have these values? Because we know principal components is actually an axis, which means that it's just a line in feature space. So if it's a line in feature space, it can be represented in a formula. As you can see, if we have the data set in two-dimensional space, and if we have this line, and it can be represented in a specific formula, right? So these values is just like the weights of the x1, x2, and xn, and blah, blah. And it's the way of things. And it's just tell us how the formula this axis has in this feature space. And how can we note how much ratio it has, or how much ratio each axis or each principal components has? Because as we can see here, if we use the C1, and it preserves the maximum amount of the variance, and then we should it will just proceed to identify the second one. Because as I have told you that the number of the dimensions, the number of the dimensions of the feature space the dataset has. And the PCA, the number of the principal components, the PCA would try to identify. And which means that if you have 10 dimensions in your dataset, and when you are applying the PCA algorithms, and it would try to identify 10 principal components. So in this dataset, on the left side, in this dataset, you would try to find 2 principal components to just preserve and just to project. So the first one for is to find the C1, this solid line, and it would project the dataset, and it will just calculate the variance. And then it need to find the second one. So the second one should be orthogonal to the first one. So it should be supposed to be the C2, the dot one. And here you can see it actually finds 2 components, C1 and C2. And this will be the result of the PCA if you apply it to this data set. So how much ratio each axis or each principal components has in its planned variance. Like, because it will calculate the variance in this axis, and it would calculate the variance on C2 also, and how much ratio it accounts for, and it will calculate them also. So this is why we have the planned variance ratio. So in the S process dataset, because we just set N2, we just N components 2. So it would find 2 principal components. And if we just call this attribute, it will tell us there is planned variance ratio along the principal component axis, and the summation of these its planned variance ratio in each axis would be 1. The summation would be 1, and it will just reflect the importance of the principal components has. So it's obvious to see that there are some missing its planned variance ratio, and maybe just 36% of it. And you can see it 45% of the is planned variance ratio, the first one's axis has, the first one principal component has. It accounts for 45% of the whole is planned variance ratio. And this is why the first one you should keep. Because what we are doing now is do the job for the feature extraction. So we will just decrease the dimensionality. We are doing this reduction job, and we should just keep the most information as we can. And we can look back here. The original data sets are 11 dimensional. And if we use the N components 2, we will just keep the original data set, and we just process it into a 2-dimensional space. Like here, as I can show you. And we can see the dimensionality it has, shape 2, right? So this is what we have done when we are using PCA, when we are using dimensionality reduction here. So it's quite simple. We just process the original one, and then it will be changed, and we will get a new data set. And this new data set will preserve part of the information the original data sets has. So intrinsically, it will change the data set, and it's cannot avoidable to lose some information, because if we just use these n components too, and we can see that we just keep in a mathematical term, or in other words, we just keep maybe like 63% of the information in the original data set. We just preserve 63% of the information when we applied PCA. Wait. And we can plot the data set now. So one of the benefits the dimensionality reduction lead to brings is that it would be helpful for us to do data visualization, because it's like it's unrealized to plot them in 11 dimensional, right? Because the only almost in most case and the most intuitive way for us to understand is to plot a 2-dimensional graph or 3-dimensional graph. And if we have 11 dimensional data sets, it's impossible for us to plot. So after we use the PCA, we just decrease the dimensions, and we just projected them to a 2-dimensional feature space, and now we can plot it. And this is one of the benefits when we use them. Like this one, you can see previously they are just in 3-dimensional, and after we use PCA or after we use the projection, it will lies in a 2-dimensional hyperplane. And so it's why we can visualize now. So any questions before we just proceed? Any question, feel free to ask. Okay, if not, and we will go on. So in other words, when we are applying PCA, it seems like a compression job. Because we are trying to just preserve as many information as we can to preserve that. And we are going to just keep them as we can. But at the same time, we are just trying to decrease the space it will take, or we are trying to speed up the training time. And it seems like a compression job we are going to do. So as we are using some compressed software like the zip or tar to compress something in our computer, and we just transfer them to other ones. So PCA just works like compression, and we can do decompression job also. So when we use the inverse transform, it will just restore the original data set. But actually it is reconstructed. So some information it will lose when we just compress it and then decompress it. It's unavoidable. But as we can see now, the X recovered, it would be as the same dimensionality as the original one. You can see here and here. They're the same, but something different because some information lose when we are using PCA. So we can compare the X recovered and the X process. And we can use the MP or close to find whether they are just the same as before. Actually, it is not. So the result is false. So some information lose. So which means some values change. And how can we just compare it? Because we need some evaluation methods. And usually we use the mean square distance to do this job, mean square error. And it would tell us how far the X recover is from the X process. So as we have talked before, the PCA would try to figure out as the same dimensionality as the original dataset has here. If the dimensionality, the dataset is 2, and it would find two components. It would find two principal components. So as we can see, the dataset we have in the code is 11. So actually, it would find 11 principal components. But here we set the n components to 2 because the other ones it projected onto would be abandoned because we don't need those ones. And so we just set that to 2, and we will keep the first 2 columns, and which is the dominant, or which are the dominant ones. And they are account for the most explained variance ratio in this PCA. And you just preserve the first 2 columns because we just want 2 columns for this project, and we just want 2 principal components of it. But actually, when we are using PCA, actually it computes all of the components, which means it computes 11 components for this data set. So how can we get 11 components? If we didn't set the hyperparameter n components, and we do this job again, we don't set the n components to any specific number, and when we call the display variance ratio attribute, and then we can get all the components we have. As we can see that there are 11 principal components, and the first one, the ratio it accounts for is 45%. And it is the same as here, right? You can see that they are the same. They are the same. But if we set n components to a specific number like the 2 or 3, which means that it will just preserve the 2 components or the, or the 3 components here. Or the 3 components here. This is why usually we will set a specific number, because we just want to preserve certain information, and we just want to reduce the dimensionality. So this is what the PCA do. And also, usually for us, we should choose the right number of principal components. We cannot choose it arbitrarily. It should depend on some things. So usually we set like the benchmark, or we have a tipping point, or 95% of the information. If the 95% of the information is preserved, and we think that this feature extraction are great, because we just keep as much information as we can. We keep 95% of the information, and it just empirical norm for us to use. And how can you do that? You can use this NP-com sum, and you do calculate that for you. And here, it will just do a summation of all of the principal components, and it would tell us, or it would tell us how many principal components we keep, and the 95% information we would have here, 6. So it implies us that it's better for us to keep 6. It's better for us to keep 6 principal components, which means that it's better for us to just set the n components to 6, n component to 6 here. It implies that. And you can see that as the dimension grows, or as the principal components we keep, and the more explain variance ratio we will keep to here. If we just set n components to 6, and the explain variance ratio would be above 95% here. Now, the largely about the PCA and the stuff about the PCA has been told already. And we can see other variants of it. Because we know, or maybe the capacity of your own computer is not good enough to hold such a large data set at one time. Because when you are dealing with millions of data sets, it's just like a great burden for your computer to hold at one time, especially for the memory. It's hard for your computer to compute them at one time. So this is why we have 2 variants. Which one is the randomized PCA, and the other one is in incremental PCA. And for the randomized PCA, you just do like a numerical way, and you would find an approximation of the first D principal components here, like it's shown here. It will find approximation of it. And it's not a closed form result. It's a numerical result. And the only way you need to do is just to set this hyperparameter as randomized. But actually, the the default set for it is auto. So if you don't need to use the randomized PCA and you just left it aside, let it be hard, you cannot just you don't need to just use this hyperparameter, because the PCA will just use a specific solver depending on the scale of your data set, actually. And the other one is the incremental PCA. And also the essence of it is quite simple. It just divide the data into mini batches and fed them, and just feed them to the PCA model, one mini batch at a time. So these two variants can help when you have like the problem on your computer capacity, but we have the cloud resource, so we don't need to worry about it now. And actually, we don't have such a large data set. So, but if you do have such a large data set, and maybe you should consider this variance also. So we have talked something, and we have finished the part of PCA. And there are no others one, because the other ones would be quite tricky. Like, actually, when we are applying the PCA here, and it's a linear projection, so it should be something non-linear. And also, we can use the kernel PCA, and you will do the jobs for a non-linear projection. And why it's important? Because we can see that maybe a line in 4-dimensional space is a line too, like a line here. But it will change if we reduce the dimensionality, because a line in 4-dimensional space would be different in 3-dimensional space. Maybe they are not parallel, and it will just swell, and it will be curved. So it's hard to say what change it would be. So maybe the features and maybe the relationship in high dimensional space would change when we apply the PCA, because we just do some change on it, and maybe the relationship would change too. So there are some algorithms to solve this problem, to deal with a nonlinear projection, and it's a kernel PCA. But we don't need to put too much attention in this meeting, because when you are going to use SVM, the support vector machine, and it will use the same strategies, the kernel tricky, like the kernel strategy. It would help you to just boost your training. And it's a tricky strategy you can use when it comes to SVM. And we can talk this strategy if we have the meeting on the SVM. And the only thing you need to know is that it will use the nonlinear projection. And you can see that if we just apply the kernel PCA, and if we apply them into a 2-dimensional feature space, and you can see this is a linear kernel. Linear kernel is the normal PCA. And this is a polynomial kernel and sigmoid kernel, RPF kernel. And as you can see, the results are totally different, right? So it depends on the final performance. because you cannot tell which one is better for you to get a higher performance once you just apply those algorithms. Because at the beginning of this meeting, I have emphasized that these are like the unsupervised learning algorithms would be part of your project, because usually you will just apply them before supervised learning algorithm. And I will repeat that again. Normally, classification and regression are seen as supervised learning algorithm, and clustering and dimensionality reduction would be seen as unsupervised learning algorithm. So this would be part of your pre-processing part. This would be the part of your pre-processing. So the final one you think is better will depend on the evaluation of the supervised learning. Like when you apply the linear regression or you apply the polynomial regression, and you will use some evaluation method, to tell the performance of the specific algorithms course, right? So it should be the combination of them to tell which dimensionality reduction way is better for you to use. It depends on the final evaluation, not just so here. And also, you can use the grid search CV to just tune your hyperparameter, and you should use some like the pipeline. And if you are not getting used to it, and you can drop it also. And also the manifold learning. Once you use the manifold learning, and you will get other totally different results also. Because as you can see that all of these data sets originated from your original data set, and they should be 11 dimensional. But if you apply projection or you apply manifold learning, and they will be reduced to 2-dimensional space, and the result would be different. And you can see here, if you use the projection, the result for the Swiss raw would be this one. And if you use manifold, the result would be this one. So it depends on the final evaluation of the supervised learning algorithms. So it's not independent actually. And this is the normal ways when we are using the dimensionality reduction. So there is nothing else I want to introduce. And I think maybe next time we can have an introduction of the clustering algorithm, like the k-means, or other things like the neural network, like the deep learning and something else, or example learning. Because if you want to do the feature, like the feature selection job, because if you want to figure out how important each feature has in the original space before using the PCA to change them. Because as we know, once we use the dimensionality reduction, it will change the original data set, because it do like something else like this. It will just reshape it, even if the dimensionality will keep the same. But like, as we can see, the relationship may be changed because we change the coordinates, because we change the baseline. So maybe something will change and some information would lose. So it's quite common to use the feature selection algorithm to keep the original relationship also. So it will be example learning, and there's nothing else. And thank you for inviting to make this introduction. And that's all.
Hello. Hello.
Yeah.
I have a question. So,
Okay.
in case I was looking into some of the papers that has used the PCA. So they also made a circular plot with the scale coordinates of the like PC1, PC2, where they are getting the clusters. So is that included in this as well? Like,
Faster.
um,
Do you
I
mean that
can
it will? Yeah.
I can show you like can I share the screen and show you like just a second. So is it visible?
Yeah.
Yeah. So this kind of clustering, like certain elements are they plot in a cluster. So this is the result of the PC principal component analysis, and they are plotting those components in this circular pattern.
Okay, let me see. Mm, Sorry, because I didn't see this graph before. I didn't know what it refers to actually.
Oh yeah, it's okay. So maybe if you find out, you can let us know.
Yeah, Wumi, I think you could send this in the Slack so that
Okay.
Sany could see this paper first before he could make some comments.
Yes, yes, yeah, I'll do that.
Okay.
Yeah.
When I have free time and I can try to figure out what it represents for.
Yeah, okay. I'll send it to you.
Yeah. Because I think that the methodology behind them are the same. And
Okay.
like the principle of it are the same. Okay.
Yeah.
So any else? So maybe we can schedule other meetings later for other algorithms, and when I'm like on vacation, and we can do more recording also. So that's all. Thank you.
Thank you, Sany.